Okay, can I start? All right.
Yep, go ahead, sorry.
Thank you, Morgan. Thank you for having me. Thank you, everyone. So today, I'm going to talk about respondent-driven sampling. Maybe most of you may not be familiar with this sampling technique, but I'm going to try to go try to explain it and go through all the definitions, and then we will go through the techniques and the methods. So this work is a joint work with Professor Eric Moody and the engaged team of Montreal and Vancouver and Toronto. So as an overview, we have recently seen a steep decline in survey participation for the last 20 years. And then the response rate has steadily declined. And so populations are becoming more and more hard to reach, or becoming hidden populations. So it's hard to conduct surveys or go deeper into this kind of population, or just collect data. So these hidden populations are difficult to access because we have no sampling frame, and there are also privacy concerns with respect to conducting studies into these populations. So we can give the example of sex workers and men who have sex with men, injection drug users, domestic violence victims. So these are hidden populations for which usually we do not have a sampling frame, and it's usually problematic to conduct surveys when we don't have prior information about these populations. So there is a need to develop reliable tools to sampling this population, mainly because we need to evaluate interventions and make sound policy decisions. So in the late 60s, in the early 60s, I say, many researchers have developed non-conventional sampling techniques to sample this kind of population. So all these sampling techniques fell under the umbrella of link tracing sampling techniques, which rely not on sampling frame, but rather on individual social relationships to reach potential participants. And one of the first authors to develop this kind of sampling technique is Goodman, under what he calls snowball sampling. So in summary, snowball sampling works as follows. So you start by selecting a number of individuals, what you call seeds. So these are usually volunteers and people you have prior information about, or that are easy to reach. So you select these individuals, and then you give them a questionnaire. You go through screening with them, and then you ask them to refer to a number of their close friends or families. And then you go through that motion. You ask those friends and families if they are willing to participate, and then you ask them, you go through the questionnaire with them, and then ask them afterwards to recruit their friends or families. So by doing that, you might be able to reach deep into the population by going further and further into the sample. But these may be effective in some cases, but there are a lot of issues around this type of sampling technique, which are mainly biased toward the more cooperative members. So that usually you have the people that have a large network of contacts that are usually overrepresented. And the second one is the issue of masking, because in this population where these population that engage in illegal behaviors, usually there are privacy concerns with referring to your friend, because you want to maybe protect your friend from legal exposures or anything of that kind. So usually you do not refer to that friend. And by doing that, you are masking that friend and potentially introducing bias to the sample. So in response to that, Erickson in '79 talked about snowball sample as convenient sample that lack any valid claim to produce unbiased and consistent samples. But he painted a rather optimistic picture in that the problems in making inference about these samples are in principle solvable by adding what he called added incentives. But he did not develop his ideas. So a couple of years later, in 1997, Douglas Heckerton, a psychology professor from the University of Connecticut, developed what he called respondent-driven sampling, which is kind of a work forward from what has been developed in the current literature on link tracing sampling techniques. So respondent-driven sampling is a form of link tracing sampling that employs what you call a system of dual incentives. So there is what you call a primary incentive, which is the reward for being interviewed, and a secondary incentive for the reward for recruiting your peers into the study. But we're going to see later how respondent-driven sampling, or RDS, differs from traditional link tracing sampling techniques. So usually you start, as in snowball sampling, with a few initial seeds, and then these seeds are given what you call coupons, so a finite number of coupons. And these are the people who are going to recruit, because so the sampling is respondent driven in the sense that the researcher is not going to recruit others, but the respondent or the seeds are going to recruit their friends into the study over a number of what you call recruitment waves. So to give a more practical picture of it, I'm gonna talk about an example of the study that we worked on, which we call the ENGAGE study. So the Canadian Institutes of Health Research and the Canadian Foundation for AIDS Research were interested in determining the factors that impact HIV transmission among gay, bisexuals, and other men who have sex with men, so called JVM. So they conducted a study between February and June of 2017, which is a cross-sectional study in 3 major cities, in Montreal, in Toronto, and Vancouver. So in this presentation, we'll focus on the study in Montreal. So in Montreal, we started with a selection of 27 seeds. So this selection was based on a community mapping exercise. And so these people were invited to a community-based survey site to complete a questionnaire and undergo testing for sexually transmitted diseases. And those who completed successfully the study receive a monetary remuneration known as the primary incentive. And so this was the recruitment wave 0. So these people were given each 6 uniquely identified coupons to recruit individuals or their friends into the study. And so we were able to track social ties between a recruiter and a new participant through the coupons, and recorded that into the database. And so through many recruitment waves, we ended up having around 1,200 recruits into the study. So this was rather effective way of recruiting individuals. And now the idea was to try to work with this data set and kind of answer some methodological and epidemiological questions. So if you can see here, this is what the 3 representation of the sample. So this is the number of the recruitment chain that started with 1 recruit that ended up recruiting around 400 individuals into the study. So you can see that this is rather effective in some cases. So now the question, I rather say, is how to conduct inference with this kind of population, with this kind of samples. So usually, because this is an unconventional sampling method, researchers were really reluctant or dubious about applying classical sampling techniques or methods to estimate means and proportions. So here, the idea in RDS in the last 10 to 15 years was rather use the network of individuals or the recruitment tree to try to compute RDS weights. So what you do is you assume that you have a population of individuals that are connected by social ties. And then in the recruitment of RDS, you have what you call homophily, because we can see sometimes that individuals with a particular trait are more tend to recruit other individuals with a similar trait. And so you have to kind of take that into account. So usually what people develop or assume that the RDS recruitment is a Markov process on the nodes of a population network that is connected. So the sampling occurs with repetitions and with infinite waves and random recruitment. So these are the two assumptions in terms of population and sampling that allows us here to develop or calculate what you call RDS weights. So what you do usually is you assume that you have A, which is the matrix of social relationships or social matrix. So A, Ij equals 1 if individuals I and J have a tie and 0 otherwise. And you define Di as the number of connections or the number of friends that individual I has in the sample. And then if you define the label SK for the individual selected at the K step. So you can use that to compute the transition matrix, which are inversely proportional to the number of friends that you have. So that allows researchers to develop what they call RDS weights. So these weights are inversely proportional to your popularity in the population. So you can see individuals who have a lot of friends are more likely to be recruited to the sample. So we take that into account by computing RDS weights. And this allows us to compute RDS estimated. So these are rather popular techniques that have been extensively used over the last 20 years. But people are more and more now shifting to multivariate methods because we want to answer compute regression techniques using RDS data. So we need to develop a rather principled methodology to do that. So if I do a brief review of RDS regression in the literature, I realized that there were no really unified framework to do that. So for example, Ramirez and al. In 2013, for example, treated the RDS sample as a random sample and applied linear regression, simple linear regression with IID errors. So some also, Johnson et al., use what they call RDS weights to take into account the design, the fact that some people are more likely to be selected into the sample than others, but treated the sample as a random sample. So Rod and McCoy, for example, decided to model the dependence within the RDS sample by assuming random effects at the seeds. So you have for each seed represent a random effect, and then you have a kind of exchangeable correlation structure for individuals within the same seed. And Spiller in 2009, for example, tried to take into account what he called homophily effects, which are really peer effects in the network. And those are different techniques to take into account different aspects of RDS. But none of these approaches usually take into account all these issues with RDS. So that's what we try to do in our study. So to do that, you need to see the structure of the RDS as a graphical structure, and then try to fit a model into using the data. So to do that, we consider, we define the graphical structure of ODS. So I'm gonna go maybe rather rapidly through these slides. So we consider an infinite population of individuals that are connected by social ties. So we assume that the population is clustered in the first assumption. So you have this clustered population. So each individual belongs to one cluster. And then the artist recruitment takes place within a subset of the cluster of the network and progresses across individual social ties. So for example, when conducting a artist sampling, so we assume that the sampling takes place within a finite number of clusters, and individuals are selected based on the ties that they have with other individuals in a population. And the third assumption is that we assume that no individual can be recruited more than once. So that differs with classical assumptions in the artist literature. So based on these three assumptions, I could give an example of what this means. So if we consider a recruitment that takes place within 3 clusters of the population, so we start by selecting, for example, 3 seeds, 1 seed for each cluster, and each seed will start a recruitment chain. So if we assume that each seed received 3 coupons, so each seed will start a recruitment chain, which ended up having 1 tree from each cluster. So this is a simple example of our assumptions and how we illustrate it. So as you can see, we end up having ODS trees. So the ODS trees are really a missing data version of the clusters, the full connected networks. So we already see that we have kind of a missing data problem, but we'll see how these materialize in our models. So in the model setup in ODS, going through the literature and based on our previous assumptions. So what we want to take into account are 2 things mainly. So the peer effects. So in the peer effects, we will assume a model in which each individual's outcome is affected by the individual value of the covariate and the mean value of the covariate of their neighbors. So this is kind of a classical peer effect models, where, for example, if I give an example, for example, if we measure this success of a student based on the number of hours of work, we can assume that the success depends on its number of hours, his number of hours of work, and the mean number of hours of work of its friends, his or her friends. So the second thing we want to take into account is network dependence. So we assume that the correlation is likely to be greater between individuals who share social ties than individuals who do not share social ties. So these are the 2 main issues we want to deal with in our model. So what we have here, the data, briefly, so we have the outcome, Yij, on the GIF individuals of the EVE cluster. So we assume that we have M clusters and Ni individual within each cluster. So we have 1 covariate, Xij, and we have also the degree of each individual, so the number of friends of each individual in the population. So these are like complete data, cluster data, and we assume a random effects for each cluster, and then we define mu ij as a conditional mean given the random effects. So we assume a generalized mixed model. So in this model here, you have a fixed effect for the Xij, for the x's, and then we have here gamma times this Dij times the sum of the covariate with the times Iijk, which is kind of the social matrix. So here we are averaging for each individuals the covariate for its neighbors. So these gamma effects take into account what they call peer effect in the model. And the delta Ij would be follow a Gaussian distribution with sigma I, and that sigma I would depend on the social matrix. So here, what we assume is that by positing this kind of correlation structure, so individuals that belong in the same cluster or have social ties will be more likely to be correlated than individuals that are non-neighbors. So this is rather a classical model in the literature. So we posit this model for the audience. And then what comes to mind is the problem of missing data, because the cluster data is a complete data per se. And what we have in ODS is really the tree data. So the tree data is that we have, for each cluster, the number of individuals that we select, Ni, and we have observed only that data. So we have Yij, the observation of the given individual on the if tree, and Xij, which is the value of the covariate. And we have also the social matrix, which is represented by the tree. So these are all kind of a missing data version of the cluster data that we have if the data was complete. So now the problem is that the social matrix of the tree is a missing data version of the social matrix of the cluster. So basically, this is the main problem, I think, in ODS. So briefly, when you have this problem, I'm just gonna go, what are the implications? The implication here is that we cannot have consistent estimators of the parameters when the data is missing in this scenario. So this is the main problem. I think that's why maybe a lot of researchers had issues dealing with regression techniques in ODS. So the consequences is that we cannot consistently estimate the parameters or the fixed effects given the observed ODS data alone, and that we cannot properly model the dependence within the network using only the social matrix of the tree. So this is the main problem that we had to deal with. So we tried to find different alternatives. We'll talk about that later. So after dealing with this problem, the next thing is to wait or not to wait. So there are have been a lot of research on survey sampling and how to conduct regression using survey data, and do we need to weight the model or not? So usually you have a design-based inference where you are interested in finite population parameters. We've seen in previously where you want to compute or estimate proportions or means. So that's a design-based inference. You go from the sample to the finite population. You also have the model-based inference where you have assumed that you have an infinite population that we have assumed for the regression technique. And you also have a kind of a hybrid design model-based inference where you try to take into account the design into the study. So basically that's the same problem that we have here. So we have a regression method, but we need also to take into account the design, the design weights into our model. So to answer these questions, so we had this interesting paper from Andrew Gelman, who talked about struggles with survey weighting and regression modeling. So the good thing is that when you kind of take into account the design into the regression, so you can claim that your results are representative of the population. But the bad side is that you will have to, you increase the variability of your estimators when you weight the model. And sometimes standard errors are more difficult to compute. But now, a general consensus on when to weight or not to weight is that, so if the weight is correlated with the dependent or the independent variables, it's a good thing to weight the model. And when you do not have enough information about the design variables, because if you have the design variable, you can just include them into the regression. And in that way, you can take into account the design. So in ODS, researchers use individual self-reported degrees to compute sampling weights, as we have seen previously. So we will see how these perform in a simulation study. So the approaches that we are using are rather ad hoc. So we tried to run some simulations to see, for example, the first thing is that since we cannot consistently estimate the gamma parameter because of the missing data problem, what happens if we ignore these effects in our model? So we have a missing covariate scenario. How are the beta one parameters going to perform? So the second thing is, if we misspecify the correlation model because we cannot properly model this dependence within the network when the data is missing, how are our parameters, how is our method going to perform? And the third thing is, we're going to use the RDS weights. So we're going to use the RDS2 weights. These are popular in the literature. And we're going to see if the degree is correlated or uncorrelated with a covariate or the outcome. How are our estimators going to perform? And the third thing is how to compute uncertainty, because if you have the weights and with it's hard to compute model-based variances or standard errors. So we use two different bootstrap approaches. What we have the tree bootstrap that have been developed by Barth and al, and a neighborhood bootstrap that have been recently developed by us. So I'm not going to go through the methodology, but what we did, we computed the relative bias and the root mean square error of the maximum likelihood estimator of beta 1 and the coverages of the 95% confidence intervals of beta 1. So usually what we did here, pretty much an ad hoc approach, and see what works and what doesn't work. And the results basically are that if we ignore the peer effects, so we induce a small to negligible bias for linear impersonal models, but we induce substantial bias for logistic regression, particularly when clustering is assumed at the seed level. So, and the second result is misspecifying the correlation model induce increasing bias for the logistic model. And the third result is that bootstrap confidence intervals yield better coverage than model-based confidence intervals, and that the tree bootstrap greatly overestimate uncertainty. So these are an interesting result. The tree bootstrap has been recently extensively used in the literature. And the fourth result is that weighted regression outperform unweighted regression when degree is correlated with the covariate. Pretty much when the weight is correlated with the covariate, weighted regression performs pretty well, at least in terms of bias. And unweighted regression performs better when the degree or the weight is not correlated with the outcome or the covariate. In that case, weighting the model only add noise to the estimators. So these are the main results. Obviously, we run simulation studies, so it's important maybe to run more simulation studies. We'll talk about that later. But I'm going to talk about today now maybe something of practical importance, the case study, the thing that we use here. So we will talk about what we call HIV treatment optimism. So following the improvement of HIV therapies, various research groups around the world have examined knowledge, perceptions, and attributes largely of gay, bisexuals, and men who have sex with men concerning these new HIV treatments. So it's important because optimism concerning this new treatment may lead to more risky sexual practice and possibly more infections. So in that regard, Van and al. In 2000 developed what they call a scale of optimism, skepticism in the context of HIV treatment. So they developed a kind of a scale of 12 items, as you can see here. So all these items were measured on a 4-point Likert scale, just to kind of measure the optimism or the perception of individuals regarding HIV treatment. So in the literature here, there were mixed findings that optimism increase risky behaviors, or risky behaviors increase optimism. So there was really a lot of uncertainty or mixed findings in the literature. So in Canada in particular, Levin and al. Found that, age, education, and income are correlated with optimism through a range of bivariate analyses in their 2017 paper. So we wanted to go deeper, more than bivariate analysis, but regression analysis using our previously developed methodology. So the question is, which social demographic characteristics predict optimism about the value of antiretroviral therapy, either as a pre-exposure prophylaxis or a post-infection treatment in a population of gay, bisexuals, and men who have sex with men? So this is the question that we want to answer in a kind of a multivariate analysis. So we went through some descriptive statistics of our audience sample. And we try to see what is the distribution of the optimism scores through age, the education, being born in Canada, and annual income. So what we have seen is that, for example, older people tend slightly to be more optimistic about about HIV treatment, and less people who do not have college degree tend also to be less optimistic about the treatment. People that are born in Canada slightly have more optimism, and people with less annual income tend also to be more optimistic about HIV treatment. So these descriptive statistics slightly are consistent with the literature. But what we wanted to do is to see, when we put all of them together in a regression model, what can we get from that? So to do that, also, we plotted the degree distribution. So the number of friends that each participant declared having. And we also compute on the right the audience weights. So as you can see, there are a lot of people that have like a small audience weight and a small batch of people that have a large number of friends. So by computing the audience weight, we see the asymmetry of the distribution. So it's important to take maybe the design of the study into account in our model. So we perform regression analysis here. So by having age, education, being born in Canada, annual income into the study, and the interaction between being born in Canada and education in a linear mixed model, in which we assume that the random effects is at the recruited level. And we computed point estimates, standard errors, and 95% bootstrap confidence intervals. So the standard errors are bootstrap standard error, as we've seen in the simulation that they perform better than the model-based standard errors. So what we have seen in this, that these are the unweighted estimators, these are the weighted estimators. So what we have seen is that by weighting the model, we see that annual income is significant and positively correlated with the optimism, while other covariates are not significant in the regression. So these give a first-hand maybe view of early results. Obviously, we did not take into account all the predictors or the possible predictors of optimism, obviously, because we could rather say that there are some risk behaviors that have an effect on optimism, or vice versa. So there are a lot of predictors maybe that we left out, but we wanted to see how the social demographic predictors perform, how do some socio-demographic characteristics predict optimism? So we can see that, yeah, so annual income significantly predict optimism here. Obviously, we need to conduct more analysis regarding this. So these are preliminary results. So obviously, we need more simulations because what we've shown are really ad hoc results because of the issues around performing RDS regression with the missing data problem. So we're still working on that. And that we also have data from Toronto and Vancouver, and we thinking about how to pull those data together and try to conduct more analysis using the data from all three cities, so that to have a more complete picture of this problem. So these are briefly what I wanted to talk about in this talk. Obviously, this is more methodology than really applied, but I hope that you might help some that are working with audience to have more ideas, more insights, and maybe more ideas to conduct further analysis. So thank you.
Great, thank you so much. That was a bit of a different perspective from what we usually hear, but I think very interesting. So I have a number of questions, but I don't know, maybe other people have a question ready. I'll jump in because I like to, I'll go first. I guess the first question I had is, so there's been talk in terms of contact tracing in COVID or in the pandemic of hesitancy among respondents in Quebec, specifically, I know about Quebec, to detail contacts that they've had because of fears of fines or something, even though public health and the fining is separate. So have you thought, or are you involved in thinking about how these kinds of strategies could be used in an evolving situation, like a public health situation, and are they applicable? I mean, this is outside of my field a bit, so I'm not sure if that's a dumb question.
Yes, that's interesting questions. So I think I've been working with a research team on how to collect data about audience and how to collect quality data with audience, because obviously we have this problem of contact tracing and that the missing data that goes with it. So I haven't been thinking about that more deeply, but I think that obviously this is the way to go in terms of collecting, because the data for COVID obviously is kind of a network data. So you have to think about it as a network data, and that people have many contacts, and you have to take that into account, the size of the network, the structure and the line structure of the networks that kind of direct the propagation of the disease. So yes, we have to take that into account. I haven't thought about it more deeply, but I know that obviously to conduct valid inference, statistical inference at least, we need really to think about how the data was collected and to take the missing data problem obviously into account. So there was a lot of skepticism in our research group about the COVID data that people are collecting. And we will rather, instead of just analyzing the data, thinking about how to better collect the data so that our analysis could be valid.
Okay, yeah, that's really interesting. So you're thinking of skepticism specifically there in terms of like the actual contact tracing system that's in place, or like these app-based contact tracing, or?
Yes, because for the contact tracing, obviously people do not report all of their contacts. So we already have that in Senegal. I went to Senegal to work on COVID, and people usually are reluctant because they don't know their neighbors to know that they have COVID. So they are reluctant to report all their contacts. And really this is a real problem, and that the data we're collecting maybe are just a missing their version of the actual true network data that we need to conduct reliable inference and effective contact tracing. So conducting analysis using COVID data, we really need to think about this more clearly, and
Yeah, and this, I mean, obviously has impacts downstream on our epidemiological modeling and the evolution.
Absolutely.
Yeah. I don't see any questions in the chat, so I'll just keep going because I have more questions. So in your sample in the case study that you showed, in terms of optimism, you found originally in the descriptive statistics, optimism higher among older GBM. And that's, I don't know if that's supposed to be surprising. I was surprised by that because my, what I thought was that it was younger individuals who now have PrEP and who maybe had not been a part of the original explosion of HIV or, the original epidemic in the 1980s and early 90s who were more optimistic. So do you think that, what do you think about that?
Yeah, absolutely. What you're saying is consistent with the literature. So I was pretty really surprised to see that in our descriptive statistics, all the people were more optimistic about HIV treatments. But I think maybe it has to do with the way we computed the descriptive statistics, because we did not weight the statistics. These are just crude statistics. So I think that has to do with that. And we also kind of have an overrepresentation of older people in our sample. So we have to, I'm thinking about, reweighting the data to see how things go. But obviously in the regression, age is not significant, maybe. So it also calls on the techniques that we're using in the regression. So it means that what we're doing is not that polished. We need more work on that. But I definitely think that age, younger people are more optimistic, but we have yet to see that in a regression model. So we need kind of more work about that. But yeah.
Yeah, it'll be interesting, I think, when you get the Vancouver and Toronto populations, because there are specificities that are geographically based, right? Okay,
absolutely.
So if there are no other questions, I'll just wait to see if anything pops up. But thank you so much for your talk. I think it's really interesting, and it has obviously a lot of implications for work that is ongoing here. So interested to see how things evolve. And thanks very much, everyone.
Thank you.
The next talk is the actual first week of February, not the second week of February. And I will send an announcement about that and a reminder on the day. So thanks very much. Thanks, Mamdou, and see you.
Thank you. Oh, yeah.
Bye.
Thank you. Bye.